Hello, it's Stat135 Lecture 8. Today the projector was not working, and so I rewrote the lecture notes on the iPad here, and I also enhanced it a bit. So please fill out whatever notes you took from class with these notes. So last time we considered nice properties of the MLE estimator, including equivariance and consistency. Today, we're going to look at how to make confidence intervals for a parameter exactly. So using paper and pencil, this is section 8.53. There are two other methods that are more commonly used, bootstrapping and large sample properties of the MLE estimator that we'll consider next time. So to make the exact calculation for the CI, we're going to have to be comfortable with chi-squared and t-distribution, which I'm going to cover now. So we define chi-squared with 1 degree of freedom to be 1 standard normal squared, which has the distribution gamma 1/2, 1/2. Furthermore, we're going to define chi-squared with n degrees of freedom to be the sum of n standard normals squared, which facts of gamma distribution must then have gamma n/2 1/2. So here's a picture of the gamma distribution. It moves over to the right as k grows because the expectation is the degrees of freedom. And so a key idea is that n minus 1 over sigma squared times the sample variance is chi-squared with n minus 1 degrees of freedom. So this is something that we're going to prove, but it is interesting because 1 over sigma squared summing xi minus mu squared is actually chi-squared with n degrees of freedom. So substituting the mu with the sample mean, actually we lose 1 degree of freedom. But that's plausible because we can see that whereas the xi minus mu are all independent, the xi minus x bar are in fact dependent. So here's a sketch of the argument that n minus 1 over sigma squared s squared is chi-squared with n minus 1 degrees of freedom. I can't prove it fully because it involves some tools that we don't have, and I don't want to take the time to do it right. But we're going to use this fact so much in this course that at least I want to give you a sketch of the proof. So you can just follow line by line here. N minus 1 times s squared over sigma squared. You can write down what this means. And the next line, so what I'm going to do is I'm going to substitute zi for xi minus mu over sigma and z bar for x bar minus mu over sigma. And then I'm just foiling and basically further simplifying, writing the sums, simplifying. And so what we see here then is that we have an equation relating a chi-squared with n degrees of freedom with n minus 1 s squared over sigma squared and a chi-squared with 1 degree of freedom. So the result is going to follow if I can show that n minus 1 s squared over sigma squared is independent of n z bar squared. So if I can show that they're independent, then the result follows. It's actually a moment generating function argument, but you guys know that chi-squares add up. Independent chi-squares add. So if these two terms are independent, then our sample variance times n minus 1 over sigma squared must be chi-squared with n minus 1 degrees of freedom, because n minus 1 plus 1 is n. And the fact that they are independent is a difficult result to prove, but it is true, and it follows from the fact that that the sample mean, which is what's in nz bar squared, and the sample variance, which is what the random part of n minus 1 s squared over sigma squared, those are independent random variables. For the proof of that, you can look at page 195, but that proves the result. Next, we're going to need the t-distribution, which is defined as a standard normal over a chi-squared with n degrees of freedom, which is defined in terms of those given by z over the square root of u over n. I'll highlight that formula. And one can show that such a ratio has the following density, but we're not gonna worry about what this density is. But if you graph the density, it looks more and more like the normal distribution as the degrees of freedom increase. And I should mention here that the degrees of freedom of your t-distribution just parallel the degrees of freedom of your chi-squared that it's defined by. So that's all I mean by degrees of freedom at this point. When we look at statistical tests, we can interpret what degrees of freedom mean in applications, but that's later. So now the way that the t-distribution comes up is by in terms of the confidence interval for the sample, the population mean. So the sample mean has sampling distribution, say as drawn here. And when you normalize this, now we don't know the population variance. So I'm just going to substitute S in for this sample standard deviation. We get x bar minus mu over s over n, which we can then write as shown here, and we see that it's a t n minus 1 distribution. So that's a great thing. Now we're ready to go. We're done with our discussion of chi-squared and t, and now let's look at what the MLE is for the mean and variance of x1 to xn normal. So that's worked out on page 269, and I'm not going to go through this straightforward MLE calculation, but the MLE for mu is just a sample mean, and the MLE for sigma is the square root of is the formula shown here, which notice is different than the sample standard deviation. So great. And I just want to mention that what we were looking for is the MLE for sigma squared, and by equivariance that is just the square of the MLE for sigma. So we have this formula here, I'll highlight it, for the MLE of sigma squared, and notice that this is biased. It's because we know that s squared is unbiased, and this is different than s squared. So now we're going to find a confidence interval for mu, and so our picture here is once we normalize x bar, that we get a t-distribution, and we can find the alpha over 2 and 1 minus alpha over 2 quantiles, of this t distribution, and here is the formula for a confidence interval for mu. Next, we're going to find the confidence interval for sigma squared, and note that n over sigma squared times the MLE estimator for sigma squared is chi squared with n minus 1 degrees of freedom. So this key fact we're going to use now. So the sampling distribution for this is shown here, and I've denoted the 1 minus alpha, and the alpha over 2 and the 1 minus alpha over 2 quantiles for this distribution. And great. So, and just pointing out that notice that this chi-square distribution isn't symmetric around 0. So when I write chi-squared n minus 1, 1 minus alpha over 2, this is the area. This says that the area, this is the point in the distribution, such that the area to the right is 1 minus alpha over 2. Okay, and I can't just write that as minus sig chi-squared over 2 alpha over 2 because it's not symmetric around 0.